Welcome to exercise 5. The first task of exercise 5 is to find out the optimal resistance to keep the PV system operating in the so-called maximum power point at different irradiance and temperature conditions. Before 6 a.m. we have a 0 irradiance. Then from 6 a.m. to 10 a.m. we have an irradiance of 300 watts per square meter. From 2 hours before and 2 hours after midday, we have an irradiance of 600 watt per square meter. And after 2 p.m. to 6 p.m., we have an irradiance of 300 watt per square meter. And after sunset, we don't have any irradiance anymore. The simplified temperature profile, we have 20 degrees Celsius before 6 a.m., then 30 degrees from 6 a.m. to 10 a.m., 50 degrees Celsius from 10 a.m. to 2 p.m., and then 40 degrees Celsius from 2 p.m. to 6 p.m. So it's not symmetrical such as the irradiance, because in the afternoon we have higher temperatures, and after sunset temperature should go down to 20 degrees Celsius. The model is given here. The voltage at the maximum power point is 32 volts. Its current at the maximum power point is 8 amps, and the temperature coefficient as well as for the power is minus 0.5% per Kelvin, and the temperature coefficient for the current is 0. So the question is which resistances we have to attach in order to keep the system working in the maximum power point. So before 6 a.m. and after 6 p.m., it's no question, there's no irradiance, so it doesn't make sense to calculate it. But here we have to find out what's the optimal resistance between 6 a.m. and 10 a.m., between 10 a.m. and 2 p.m., and from 2 p.m. to 6 p.m. Same as in exercise 4, we make a draft of the temperature and irradiance profile. So the dashed green line is the irradiance value. Here 300 watt per square meter until 10 a.m., then 600 watt per square meter until 2 p.m., and from 2 p.m. to 6 p.m. we have 300 watt per square meter. After sunset irradiance is 0. For the temperature here we have in red, we have 30 degrees in the time frame between 6 a.m. and 10 a.m., and then it goes up to 50 degrees Celsius from 2 hours before and 2 hours after midday, and then from 2 p.m. to 6 p.m. we have 40 degrees Celsius, and then after sunset 20 degrees Celsius. So we make a case separation as in exercise number 4. Case 0, what's not of interest because there's no irradiance. Case number 1 from 6 a.m. to 10 a.m. Case number 2 from 10 a.m. to 2 p.m. and case number 3 from 2 p.m. to 6 p.m. and after 6 p.m. is case number 4. Let's start with case number 1. This is again the description of the task. To find the optimal resistance, it's just the voltage in the maximum power point divided by the current in the maximum power point. If we take as an example for the standard test conditions where we have 32 volts and 6 amps at 1000 watts per square meter and 25 degrees Celsius of module temperature, then we have here 32 volts divided by 8 amps, that's 4 ohms. If we have other temperatures, we have to make an adjustment factor here according to the temperature difference. And also for the current is directly proportional to the irradiance. We have to find out what's the actual irradiance in relation to the irradiance under standard test conditions. And as you all know, irradiance under standard test conditions is 1000 watt per square meter. And the temperature difference is the actual temperature minus the temperature under standard test conditions, which is 25 degrees. So case 1, we have a reduced irradiance compared to standard test condition irradiance to 300 watt per square meter. cell temperature is slightly elevated from 25 to 30 degrees Celsius. And if we put it in the formula, we have here the voltage under standard test conditions, 1 plus the temperature coefficient minus 0.005 per Kelvin, and temperature difference of 5 Kelvin divided by 8 amps, then 300 watt per square meter divided by 1000 watt per square meter. That's 13 ohms if you put all in the right numbers and calculate the result. Let's go to the next case, case 2. There we have an irradiance of 600 watt per square meter and an elevated cell temperature, which is 50 degrees Celsius. So we have here 32 volts times 1 plus minus 0.005 per Kelvin times 25 Kelvin divided by 8 amps, 600 divided by 1000, so 0.6 is that. So this is 0.6, and this is a temperature adjustment factor 0.875, and together the outcome is 5.83 ohms. So we have to reduce the resistance drastically in order to still keep the operation point in the maximum power point. Let's come to number 3, case number 3. Same formula here again. There the irradiance is reduced from 2 p.m. to 6 p.m. Temperature is a bit elevated, so we have 40 degrees Celsius compared to the morning. And if you put in the numbers here, we arrive here at 12.33 ohms. If you compare it to the morning numbers, you see that here the resistance is slightly reduced due to the reduced voltage. That's it for task number 1. Let's come to task number 2, part number 2, DC wiring. So we have to calculate the maximum number of modules and the according power output of a strings of modules. We have to make sure that the voltage under most extreme conditions stays below 1000 volts. And the most extreme conditions are that we have open circuit conditions instead of conditions in the maximum power point, and in winter when it's very cold and after sunrise, module temperature might be at minus 20 degrees and therefore voltage is highest, and we have to calculate that extreme case. So we have here all the required data. What we have here, we have open circuit voltage 36 volts, and we have to consider the increase by the low temperature. Next question was, what is the minimum diameter A of a Cooper cable from a string of modules to the DC connection box if the maximum permitted cable loss is 0.5%? The modules are attached to each other. The series connection is carried out via the pre-installed cables and connectors. These are all included in the data sheet here, so we don't have to consider them. And what we also know that the DC connection box is 5 meters away from the PV string. Third question is, what would be the gain in generated electrical energy for a 1 megawatt peak system during its lifetime for a system voltage of 1500 volts and of 2000 volts if you would use the same diameters as calculated above? So due to the higher voltages, the current will be reduced and therefore we would have less losses, and we have to calculate the advantage of those compared to the additional costs for the cables or the insulation, because it has to vary higher voltages. So we have here the yearly irradiance here is 1176 kilowatt hours per square meter per year. The performance ratio is 0.85. Last but not least, we have to calculate that financial advantage for the voltage increase. If we consider additional insulation costs, for example, if we increase the voltage from 1000 volts to 1500 volts, we have to spend 0.1 euro per meters more. And if we go even to 2000 volts, we have to spend 0.15 euros more per meter. The Cooper diameter stays the same, so the Cooper cost is the same for all the voltages. Further, we have to consider that we have a power purchase agreement for the sold PV electricity of 8 euro cents per kilowatt hour. We take also for granted that the installation costs for a system voltage of 2000 volts are double than for 1000 volts, and the cable process Cooper price is about 10 euros per kilogram. This we need to know because we have to calculate also the price for the Cooper cable. So this is our configuration. So we have a lot of modules interconnected in series to our string. The number of modules we still have to calculate. So here's the number n. And they are mounted in such a way that the short side is below, and so a short length is below. So if we put them all together, the cable here has to be extended by 1 meter. For example, if we have 20 modules, we have 20 meters here. These interconnection we don't have to consider because these are carried out with the pre-attached wires already. So we don't have to calculate, but these going from here, from the minus pole, from one end to the DC connection box, we have to consider, for example, n is 20, we have 20 meters here, and then additional from the end of the PV power plant to the DC connection box is 5 meters for the minus pole and 5 meters for the plus pole, so altogether 10 meters. Additionally, we should consider the inverter, but this is not part of the question here. This cable wiring would be a separate task. And then from the inverter, we have then a grid connection. So the cable loss are calculated as follows. So we have the voltage loss along the cable times the current flowing through that cable. If you calculate the voltage loss, here is the resistance times the current through that cable. And if you multiply it once again by the current through the cable, we have a cable square. The resistance of the cable is the length of the cable. So this plus this plus this. Then divided by its diameter times the conductibility. So if we put that in, so we have here the cable loss is L times I cable square divided by the square area of the cable times the conductibility. And if we put it in relative terms, the cable loss divided by the total power, we have this formula. So we have here additional the system voltage times the I cable is our system power. This gets eliminated here. So we have just L times I cable divided by A times key times system voltage. This is just a repetition from the lecture. So you have this transparency here where it shows the formula once again, and here we have the electrical conductibility of Cooper. This is 56 meters per ohm per square millimeter. For aluminium we don't have to consider, it's only asked for Cooper wires. So here a first task is what's the maximum number of modules in order to keep the system voltage of that system below 1000 volt. That's important because if we go beyond 1000 volts, we have different standards and different safety requirements. And also some of the subsequent components, for example, a charge controller or most often a grid inverter, they have a certain voltage limitation and we have to consider it. And if you would go beyond a certain voltage, it even could be damaged. So let's calculate that with the given data. So we have here the voltage, open circuit voltage. We have to calculate now the open circuit. This is the open circuit voltage under standard test conditions at 25 degrees Celsius. So now we have to calculate at minus 20 degrees Celsius. So we have a difference of 45 degrees. And while it's negative, the difference we have up and the temperature coefficient also negative, we will have a positive increase in voltage. So we do this here. This is our formula. So this is the temperature coefficient with the temperature difference. T2 is minus 20 degrees, minus 25 degrees. So if minus 45 degrees, temperature coefficient as given here is minus 0.5% per Kelvin or minus 0.005 per Kelvin. If we have temperature differences, we can substitute this degree Celsius to Kelvin. So we have Kelvin divided by Kelvin, then we just have a number, that's good. And so we have here adjustment factor for the voltage. We put it into a number. So we have here this adjustment is 1.225. And if you multiply this by 36 volts, that's the voltage under standard test conditions. The outcome is 44.1 volts. So we have 1000 volts maximum. So we have to divide this 1000 volts by this 44.1 volts. The outcome is 22.68. So that's the maximum number of modules. So while we have full modules and we don't want to exceed 1000 volts, the maximum number of modules we can actually use is 22. For those 22 modules, so N max is 22, we have 22 times 8 amps times 32 volts. We have a power of 5.632 kilowatts. If you would increase the voltage, we can put together more PV modules in a string. So it's 1500 volts divided by 44.1 volts. So we have 34 modules. So that's quite convenient because it's very close to the maximum. So we don't lose here 0.68 modules. So we can really use 34 modules. Then the power of such a string would be 34 times 8 amps times 32 volts, which is 8.7 kilowatts. If we would even increase the voltage to 2000 volts, we would be able to put together 45 modules in series conditions. And that would lead to a power of 11.52 kilowatts for those 45 modules. Next task is to find out the cross section of a cable at the 1000 volts required. So the relative power of the cables from the modules to the DC, the power loss should not exceed 0.5%. So the maximum loss is 0.5%. That's we calculate. So that's a formula already given in the lecture, and we saw it already before. So it's the length of the cable times the current going through that. And here, this is a relative cable loss. This is 0.005, equivalent to 0.5%, times the conductibility of the cable, times the voltage of the system. So if we put in the right numbers now just for a single module, so we have 32 meters, 8 amps goes through that because it's all in series. So we just have to have a single current. But here for the 1000 volts, we have 22 modules and the voltage is up. So the voltage and maximum power point is 32 volts. So we have 22 times 32 volts. And this is the loss here, 0.005, and the conductibility of the Cooper cable. So we arrive at a cross-section area of that Cooper cable of 1.3 square millimeters. Third task is what would be the gain in generated electrical energy of a 1 megawatt system during lifetime 20 years for a system voltage of 1500 and of 2000 volts if you would use the same diameter as calculated above. So we have this irradiance value 1176.5 kilowatt hours per square meter per year and a performance ratio of 0.85. So we calculate the length of the cables at 1000 volts. We have 22 modules. Remember the scheme here. So we have here 22 times 1 meter and plus 5 meters. And for the other modules, if we have higher voltage, we have more modules here. Accordingly, we have more length of wires here or cables. So here we have this. So 22 times 1 meter is 22 meters plus the 2 times 5 meters. Altogether, we have a cable length of 32 meters. While we want to have a power plant of 1 megawatt, it's not enough, one single string. So we have put additional strings in series. How many strings are those? So one string has the power of 5.632 kilowatts. And the number of strings is then the power of the power plant divided by the power of a string. So it's 1 megawatt or 1000 kilowatts divided by 5.632 kilowatts. That's 177.57 strings. While we want to have at least 1 megawatt, we have to round up here. So it's 178 strings we need there. The according cable length is 178 times 32 meters. What we calculated here is 5,696 meters. Let's go to the other voltages here. First, we calculate the losses here. So at this length, we put in here the length, and the current is still 8 amps. The diameter we calculated 1.3 square millimeters. The conductivity is the same. So we have here a loss of about 5 kilowatt. What you have here, or in other terms, relative losses is 0.0049995. We wanted to have less than 0.5%. That's correct. Then the PV generation during that time period. So we have 20 times, and this is not this cross-section area. This is the area of our PV power plant. And W irradiated by 1 year. So this is the irradiance arriving on our power plant during 1 year. That's a performance ratio 0.85. And this is the conversion efficiency of our module under standard test conditions. Let's calculate that quickly. That is the power under standard test conditions divided by the area under standard conditions divided by the irradiance under standard test conditions. So the power is 32 times 8 amps. The area is 1.6 square meters, and the irradiance under standard test conditions is 1000 watt per square meter. So altogether we have an efficiency of 16%. The energy, photovoltaic energy during 20 years, we have here 20 times 1.6 square meters times the irradiance value during 1 year times the performance ratio and the conversion efficiency. Altogether we get from this generator during 20 years 5,120.23 kilowatt hours. This is just of one module, sorry, not of this generator, but of one single module, 1.6 square meter. We get during 20 years, we get 5,120.23 kilowatt hours of one single module with an area of 1.6 square meters. So we calculate the losses during 1 year. Yes, then a thing is not given, so we have to take into consideration two extremes because the current is quite different at those two extremes. We have the full irradiance at 1000 watt per square meter. That's the maximum irradiance we can achieve. And this occurs to 1176.5 hours during a year. So this multiplied is our irradiance values of 1176.5 kilowatt hours per square meter per year. So we expect here the maximum losses while the current is highest for these conditions. The other extreme is if we take the irradiance extremely equilibrated during 12 hours for the whole year. So we have 4,380 hours, so that is half the hours of the year. Then we have the total irradiance value. This would lead to 268.6 watt per square meter. So only about a fourth of that value, and accordingly a fourth of the current. Let's take a look at the losses of what we have here. So we have the total length of the cable of our PV generator, the duration where this occurs, and the the amps what we have here, and the cross section and the conductibility, and altogether we have 5,891.32 kilowatt hours of losses. If we take the more equalized irradiance value, then we have 365 times 12 hours of irradiance of duration, and the current is much less. As mentioned here, it's only a fourth, so 2.149 amps in square, divided also by the cross-section area times the conductibility, and we have 1,582.44 kilowatt hours. So the number of strings we have to put in parallel to build a power plant with 1 megawatt, we calculated already, that's 178 strings. If we go up to 1,500 volts, while we need less strings for that, because one string has more modules, we only need 115 strings. If we go up to 2,000 volts, then in each string we have 45 modules and a power output of 11.5 kilowatts. So altogether we need less strings, so it's only 87 strings. So the cables required for that, for one string at 1000 volts, we calculated that already 32 meters. Then we have to multiply it times 178, because this is our number of strings. So we need 5.7 kilometers of cables about. So this is our number for 1000 volts. If we go to 2000 volts, then we have a lower number of strings, but while we have more modules there, we have to consider more cable here. So it's reduced, but not really very much reduced, about 10-12%. And if we go to 2000 volts, same issue. So we have more modules in the strings, and we have less strings, where we have only 87 strings times 55 modules, 55 meters, 45 meters plus 10 meters. So altogether we have about 4.785 kilometers of cables. So the losses, what we occur, we calculated here already. We calculate already for 1000 volts. Now we will calculate them for 1500 volts. Same issue here. We have less cable length here a little bit. So these losses are a little bit reduced compared to those at 1500 volts. And here at the other conditions where we consider a more equalized irradiance distribution during the year, we have 1405.94 kilowatt hours of losses during 1 year. If we go to 2000 volts, we just put in the right numbers, so we have less cable requirements and accordingly less losses. Same issue for the more equalized irradiance. We have here only about a fourth of the current and accordingly a fourth of the losses here, so we have about 1329 kilowatt hours. So now we do the financial calculation. We have to consider, if we calculate the cable costs consist of the cost of the insulations, KE, and the cost of the copper inside the cable. What we know already from the given task here, that the price increases by 0.0 euro per meter for a voltage increase from 1000 to 1500 volts, and the cost of the insulation would increase by 0.15 if we increase from 1000 to 2000 volts. Let's put in a formula here. So we have here KE 1000 volts plus 0.1 euro per meter is the cost of 1500 volts. And for 2000 volts is the cost of the 1000 volts plus 0.15 euro. We take for granted that the insulations costs are proportional to the maximum system voltage. So we take this, I think it's also written here, I think it was written in the beginning. So we have here the cost for the insulator at 2000 volts is double than the cost for 1000 volts. If you put it in a formula here, we substitute this by that. So we have 2K 1000 volts is equal to KE 1000 volts plus 0.15. So we divide it by KE 1000 volts. So we have KE 1000 volts is equivalent to 0.15 euro per meter. Then we know this, that we increase the cost by 0.1 euro per meter. So we have the cost of the insulation for 1000 volts is 0.25 euro per meter. And for 2000 volts, we know already 2 times the cost of 1000 volts. So it's 0.3 euro per meter, or we calculate by that. So increase of 0.15 euro per meter. So 0.15 plus 0.15 is 0.3 euro per meter. That's our insulation cost. So we come to the copper costs here, next task here. So we look up the density of copper. So the copper density is 8,920 kilograms per cubic meter. So 8.9 times more than for water. And the volume of 1000 meters of copper cable is the 1000 meters times 1300 cubic millimeters per meter. So we have here a 1.3 10 to a power of 6 cubic millimeters, and then it's 1.3 to a 10 to a power of minus 3 cubic meter. Then we have the mass here of 1000 meters. It's the density times the volume. And then if you put it here, this gets eliminated and we have just kilogram, and this is 11.596 kilograms for that. While we know the copper price of, what was given the copper price, I think it was given at 10 euro per kilogram. So we have this times 10, so we have 115.96 euro for that. And for per meter calculated, it's 1.1596, or rounded to about 0.116 euro per meter. The full cost is the insulation plus these copper costs. We have here for the 1000 volts, the insulation is cheapest. Copper price is all the same for all 3 options because we keep the same diameter of the copper wire inside, the conductor inside. So we have here final costs here for the 1000 volt option is 26.6 cents per meter. For the 1500 volt options is 36.6 euro per meter. And for the 2000 volt option, it's 41.6 cents per meter. So those cable costs for total cable costs for all the wiring needed for our 1 megawatt power plant for 1000 volts is here. We have a length required of 5,696 meters, and that's the specific costs. So we have a total cost of 1,515.14 euro. And for the 1,500 volts, we need less length, but due to the higher insulation costs, we have an elevated price for all of that. On the other hand, we should have we have less losses, and let's see whether it compensates. And the cable costs for the 2000 volts option, so we have less length but higher costs for the cable, so in altogether slightly increased costs of 1,990.56 euro. So let's calculate the financial value of the reduced cost for the 20 years. So we have first, we calculate per year. So we have the benefit we have if we generate more electricity, we can sell that electricity at a price of 8 cents per kilowatt hour. Let's see, so we have the losses of 1000 volts and the 1500 volt. Let's take the difference. We have now, there's a negative difference multiplied by 8 cents per kilowatt hour. So we have negative costs. That's a benefit of 52.63 euro per year. This is for full irradiance. This is worst case, so the highest losses are there. And if we take more equalized irradiance, then if you put in the numbers here, you will have less losses, but also less benefits by that voltage. So the benefit is only 14.14 euro of negative costs per year or benefit per year. For 2000 volts, same procedure. Then we arrive at 75.38 euro per year of benefit for the full irradiance calculation. And if we take an equalized irradiance during the year, we would have 20.32 euro per year only. So let's put all this number together, the total value. So we have here the savings is a negative cost difference, and that is here the cost of the increased voltage minus the cost of the standard 1000 volt option plus the cost of the 20 years of savings, what we have here, also negative costs. It will be negative cost, but here's positive cost, and then we put a negative value in here. Let's start with the 1500 volts option. So we have here cost of 1000 volts is a bit higher than minus 1000 volts, so it's a positive value, and here we have savings. Negative cost is a negative value. Let's see. So we have here 1515 minus 1851.96 plus the negative value plus the positive savings. We have here savings of 685 euros. For the equal irradiance, we have a negative difference here. So we have here the saving is negative. We don't save anything. We have costs, additional costs of 55.42 euro during the lifetime of 20 years. Last but not least, 2000 volts. Let's take a look at the savings. They are biggest here. This is 1032.13 euros. We spend more on cables, but we save also more. And for equal irradiance, the savings is also negative, so we don't save anything. We put that as a result. We see that if we have intense irradiance, not for all time of the year, but close to 1000 watt per square meter, then we have some advantages for the higher voltage levels. But if we have more equalized irradiance in the vicinity of 280 watt per square meter in average, then the advantage is diminishing. It even can be negative, the advantage, so we have additional costs. So therefore, in order to carry out a more detailed calculation, the irradiance level / probability distribution should be given, and then we could really do more detailed calculations how much the costs are. We just took the two extreme here in this case. That's it. Thank you very much for listening.